Hello, good morning, good afternoon, good evening, depending on your time zone. Welcome to the CMCC webinar. This is part of a series that CMCC wants to offer to the community as a platform for discussion on climate change issues, interdisciplinary issues ranging from dynamics of climate to the social and economic problem involved with climate. If I can get next slide, Rich, please. CMCC is a no-profit foundation that has the mission to investigate the climate system and its interaction with society, to provide rigorous scientific results in a non-advocacy mode in order to investigate and develop adaptation, application, and also evaluation of mitigation policies and adaptation policies. Next slide. With a network of laboratories placed in Italy, these are the cities where we have major laboratories in Lecce, in Capua near Naples, in Viterbo near Rome, in Sassari, in Bologna, Venice, and Milan. We do have a major supercomputer on which we do most of our calculation that's sitting in Lecce. Next, please. And this is our research divisions that are basically designed to attack all the problem of all the different issues of climate change, starting from the development of the software infrastructure in our advanced scientific computing division, to the development of the climate simulation prediction, development of the models of atmosphere and ocean, and also estimation of the ocean states through our data simulation effort. And then we have divisions that are working on the impacts on agriculture, forest, and ecosystem service, regional models, hydrogeological impacts, and then more socially oriented investigation that involve risk assessments and adaptation strategies, and of course, economic analysis of climate impacts and policy. Next, thank you. And of course, these are the topics that we try to address. The main idea is that we try to provide an integrated place where we can look at all the different aspects that are involved in understanding the climate change problem, or in general, the climate variation problem. We also do, for instance, seasonal forecasting, seasonal predictions, studies and operations that are involved with the investigation of climate variation and its impacts on the society. Next. We have a number of outreach events, publications. We collaborate with a number of universities for high degree programs. We do have a PhD program in climate science, in science and management of climate change with the University of Venice, Ca' Foscari, and we do also a lot of communication that are described in detail on our website. Next, Rich. Great, so let's go straight to the issue today. The seminar, the speaker today is Rich Neale from NCAR, the National, sorry, that's not good. The National Center for Atmospheric Research in Boulder, Colorado. And Rich has a PhD in tropical meteorology that he got at the University of Reading, where he spent a couple of years before moving to Boulder. And well, I can understand. Boulder has a much better climate than Reading, that's for sure. And he has been there since. He's been a very active presence in the development of the NCAR community model, first working on the convection modeling, and then becoming very active in the number of issues that go from the subseasonal modes of variability, the mid-diurnal oscillation, the diurnal cycle, and blocking. He has chaired the atmospheric modeling group for the NCAR community assistant models, and he also received the CESM Distinguished Achievement Award because he's been one of the driving force behind the development of the model. And today he will give us a very interesting talk, I think, on how the systematic error of the model has evolved over the years, This is a very important piece of information that really, in some sense, is central to our work with this climate model. So he will give a talk of about 30 minutes, correct me if I'm wrong. Then after that, we will have a question and answer session. You all guys that are listening, you can send your questions using the chat box in your webinar screen, and please, when you write the question, state your name, your affiliation, so that I can report the question to Rich after the end of his talk. And I think that's all I have to say, so I will definitely leave the floor to Rich Neale, please.
Okay, thanks, Antonio. I hope everyone can hear me. It's really nice to be able to talk to the CMCC and wider community on a few things we've been doing at NCAR. So, excuse me, just move this. Okay, so yeah, I'd like to talk about bias in the NCAR community Earth system model and how it's evolved in the past and the kind of tough choices we're having to make with respect to most recent CMCC development activity. And here on the left, we see a few of the kind of people who have been critical to the development process for the model over the past 50 years, essentially. So I'll start with this kind of provocative comment, and it's driven me to a certain extent over the past few years in development, made me feel, at least the top part of it, made me feel a little bit more kind of comfortable with what I'm doing. So all models are wrong, but some are useful. I mean, everyone would kind of acknowledge that. And I looked this up a little bit, and it was kind of derived from this larger comment from George Box, the British statistician. And if we read it out, it's a little bit more worrisome. It says, since all models are wrong, the scientists cannot obtain a correct one by excessive elaboration. On the contrary, following William and Occam's razor, he should seek an economical description of natural phenomena. Just as the ability to devise simple but evocative models is the signature of the great scientist, so over-elaboration and over-parameterization up the mark of mediocrity. And so I read that, and my first response is like, oh dear, from the climate modeling perspective, because, you know, what's been happening over the past 10 and even greater number of years is this huge increase in climate model complexity. And CSM is and CSM2 in particular, the most recent version of the model, is no exception. And I'm sure most people have seen figures like this, which show the evolution from essentially the 1960s, a much more simple atmosphere focus with some ocean model, through a huge raft of enhancements and complications and increases in complexity through to the present day, where, you know, we're really considering in the whole Earth system model, ice sheets, ecosystems, etc. And you know, this is not without reason. You know, we're looking for new science. We believe there are improved and missing processes we need to include in terms to have a more complete description of the Earth system. But of course, the consequence of this is you have new interactions, new constraints. You maintain the old constraints, which is, I don't think, often wise people don't appreciate. And as an example, in CSM, you know, a cycle or two ago, we really improved the El Nino. We didn't have a very good El Nino. We really improved it. You could argue we got it for the wrong reasons, but that's by the by. But once you have something like a good El Nino, even when you add all this complexity, the expectation is you do not lose that good El Nino. And so that's an additional challenge on top of all the new developments. And it's fair to say, and I'll show a couple of examples at the end, CSM2 development has encountered problems with most of these recent inclusions, ice sheets, biogeochemistry, etc. And I'll talk about that later. So on the whole for this talk, it's kind of motivated by reaching the end of CSM2 development and trying to answer the question as you approach writing the papers, that overview, the whole system, particularly from the atmosphere perspective, is CSM2 a better model than CSM1? That's kind of easier to write. But a larger question that started to occur to me is CSM2 better than all previous models? Your order zero expectation is yes. But as you'll see, that's not, in many cases, not the case. And the way I looked into this was to go back over all the years, in 35 years in general, but for this particular talk, it's over the previous 20 years, and have we improved? And you can say up front, I'll say, in the blue here, there are clear monotonic improvements in certain aspects. There are persistent biases that remain even from 20 years ago. Skill in certain things go up and down. Previous versions of the model were better in certain aspects than the current version. And there are trade-offs associated with this. We make decisions in terms of including certain improvements that were at the detriment to certain skill. So for the majority of the talk, I'll talk about aspects of the mean climate, a little bit on variability, which is my kind of area of interest, and I'll contrast a little bit atmosphere only, EMIP type, for a couple of configurations, and as I said, I'll finish up with a CSM2 couple of examples of development and challenges. So the NCAR model, where did it come from, and what's the kind of evolution over time? So in the 60s and 70s, there are various versions that were begun by Akira Kasahara and Warren Washington, which evolved in the early 80s into a climate type model, and then from just the atmosphere and through starting with coupled models in the 90s, there's a vast array of evolution of models with various acronym soup, essentially evolving from climate model CCM0 all the way through to our current incarnation. So CAM6, which is just the atmospheric part of the model, and CSM2, which is the fully coupled version of the model. I'll talk a little bit in these later versions in terms of variability. But in essence, the green models here are the ones I will talk about today. I have the data for, so it's really a data mining exercise, a paleo exercise, to go back and find and extract data from strange formats, but I managed to do that. All right, so your first question is, have we improved? So here I'm showing from AMIP simulations, so these are prescribed, observed SSTs, no ocean model. And so this is a simple forecast type metric. So it's an error metric for the 500 millibar height in the northern hemisphere. And I'm not going to focus on it, but these are various contributions to that error. So here we're talking about all the atmosphere models I've focused on. Left to right is old to new. And so it's kind of tale of two seasons. In DJF, the climate error is low, and we're essentially we have this monotonic improvement. So that's nice. This is focusing mostly on baroclinic systems in the mid-latitudes, and we've done a very good job of that and improving that throughout the evolution. But in June, July, August, you can notice two things. The error skill in general is high. The error score is high, but the evolution is not monotonic. So, for example, CAM2 is better than CAM3 for this metric. And then in annual kind of, essentially, thankfully, DGF and other seasons win out. So CAM6 just squeaks at being the best, but that's not necessarily by design. So, but the summary is some things are monotonic, other things are not, and I'll go into a little bit more detail. One example, I think that in particular that has been focused on over the whole evolution, 20 or so years, is of course the precipitation, and in this case the ITCZ. And here I'll show a few of these as these colors here. So bottom to top are old to new, so CCM3 to CAM6. This is a zonal mean precipitation, seasonal mean, DJF on the left, JJA on the right with some observations. And so, your first look is that, okay, it's not changed that much in terms of we did a good job initially 20 or so years ago, and we're still doing a similarly good job. I'll show details in a second. Another thing to notice, and I think it's common across many climate models, all the evolution in terms of the mean precipitation here in both seasons is too high. So that's a persistent problem that remains, is we just cannot get the right, if you believe any of these data sets, essentially, we cannot get the right precipitation in the mean. So focusing a little bit more now on the biases. So this is just taking those previous plots and then looking at the difference compared to GPCP data set in this case. So a few things to know. Again, these are all the model versions, bottom to top, old to new, CAM6. And so I'll point some things out in terms of the biases. So this bias, this excessive precip bias in the northern hemisphere, just north of the equator, I mean, there's not a monotonic change. It's interesting that the bias came in CCM3, it kind of went in CAM2 and CAM3, and then it came again in CAM4, and Cam 5, and then Cam 6 we're back here doing a pretty good job, but it's still about as good as Cam 3. It's worth noting. Second thing is, Southern Hemisphere bias, this SPCC type bias, is barely improved. And in fact, the best case we got for it in wintertime is Cam 4. So that's persistent bias. If we switch to JJA, it clearly is a very much more mixed bag. I'm not going to talk into detail the different differences here, but really, quite clearly, there's a back and forth in terms of the precipitation biases among the model versions. Hard to pick out necessarily that Cam 6 is the best everywhere, but essentially, you know, it's much more heterogeneous. Monsoon has a much greater role, of course, and then a lot of this bias is an ITCC width bias. And another persistent bias that I didn't really appreciate is this Northern Hemisphere extratropical bias has been quite persistent and has not really improved in the past few model versions. Let's contrast AMIT versus coupled. So it's just focusing on GJF here. So the particular location of the bias that we talked about that was persistent in AMIT is not a maximum here in the coupled version. So there's a shift there in terms of the bias. The bias that we see, we really have seen a very good improvement. So that's a kind of something we would like to, you know, a check mark is that CSM2 and 1 really has resulted in an improvement here. And the location where biases are, the location is pretty similar. The couple versus AMIT, the evolution of the bias is very different in terms of whether a particular model version was better than the previous one. So again, the heterogeneous behavior associated with the coupling is pretty large, and the high latitude biases don't change that much. So that's a kind of water cycle, a few notes on that, trying to understand how the biases evolve differently. A couple of examples I've shown now, of course, more recently in terms of couple models recently, at least 10, 15 years, there's a necessity to get the clouds right, and in particular the cloud forcings, and because of that, of course relates to forcing the coupled system from the perspective of the impact of aerosols more recently, and also from the impact of feedbacks. So what are the response of cloud forcing and clouds to increases in surface temperature, for example. And here I'm showing the evolution of a good example that's kind of mostly monotonic is the shortwave cloud forcing. So the impact, the radiation of low clouds, and just to give you an example of how this is a monotonic improvement. So if we can just zero in on root mean squared error, we're talking around 13 for Cam 2. We don't have it for CCM 3, back down to 9.5. But in the face of that, there is a lot of shift in the bias in terms of what's happening in the tropics, and then suddenly in Cam 4, for example, there's a bias at high latitude. So it's not a monotonic change everywhere. There are big shifts, but the net result for this is positive. Another associated variable is a long wave cloud forcing, and so that's more related to high clouds, particularly in the tropics, and ice cloud processes. Very difficult, challenging process in terms of ice habit, for example, and the impacts with aerosols. This has been not a very good success story in that root mean squared error, like for like, it is actually worse in Cam 6 than Cam 2 20 years ago. So that's pretty startling. I had not really appreciated that until I started looking at this. And the bias in general switches from the tropics essentially to higher latitudes. And that may be an improvement that could be identified in terms of process, but overall it's a degradation. And you can kind of like do this kind of skill scoring for, obviously it's very simple skill scoring for a lot of variables, many variables. And this is just a selection of the few as we vary from CCM 3 out to Cam 6. And we can see, for example, we're showing the evolution of skill, so the root mean squared error is shown. Red is essentially the worst of all the models along a particular line, and green is the best. So comfortingly, and maybe not surprisingly, precipitation has really evolved from something that was high root mean squared error here to the lowest here. So that's great. We focus on that a lot. It's comforting. But they're not necessarily all the reds on the left and all the greens on the right. And as I just showed, for example, long wave cloud forcing in this particular metric at AMIT, the green, the best is in Cam 2, and the worst are in later model versions. So, but in general, you know, the reds are on the left, greens are on the right. So overall, we're improving. Couple of examples, more examples I'll show you, which are pretty stark in terms of the change in model version and the change with respect to season. So this is just precip, seasonal precip over the US. NCAR has to get this right. And we can see here the general bias throughout the whole evolution of these models, CCM3 to CAM6, is that we're improving. I mean, it's small improvements, but our bias in the southeast US, the wet bias, is pretty good. In CAM6, really reduced quite a bit. And also our kind of transient system, if you like, bias in the mountains and on the coast of the US is really come down from 5 to like 2.5 millimeters per day. So I think great, very obvious systematic biases. Okay, let's look in summertime, and you throw your hands in the air to a certain extent. That we from CCM3 and CAM6 look kind of similar, but in the middle we've seen this whole switcheroo between like negative biases, positive biases over Colorado, for example, right here. But it's disappointing that the same kind of changes have not resulted in summertime improvement in biases. And there are many reasons for that. It's much more challenging, as I'm sure many people will appreciate. The summertime precip in the US is associated with organized convective systems, and the resolutions we're running at right here, which are only of order nominally of all these of 1 degree in the atmosphere, are not really expected to pick this up. But nonetheless, it is somewhat disappointing. So my one variability example, like as I said before, like tropical variability is my kind of area of interest, and in particular the man-June oscillation. And this is most recently, in particular, has been a focus in climate models, particularly as they start to be used as in terms of subseasonal to seasonal prediction. And so its importance in many interactions with many modes of variability, for example, has been acknowledged. But the challenge for a climate model is it's somewhat of an emergent phenomenon, so it's kind of an aggregation of convection and the large scale flow, and so it's a challenging phenomenon to represent. And so I'll show one slide of this. It's a little bit busy, but I think it illustrates through the colors the evolution of skill in this particular phenomenon. So the simple thing to take in is that this is a particular metric of the man-June oscillation. And all you need to really take in is that, this principal components of the variance explained by the MGO part of the mode is increasing for the first mode along the x-axis and for the second mode along the y-axis. So essentially, if you're up where Euro-Interim and Merit are for this particular metric, then that's close to observations, obviously. And if you're down here, then you're doing a poor job. So, and here's the evolution of the recent models, 3, 4, 5, 6. And then there's a description of the things I think have resulted in improvements. And so it's very clear that, there is a change in skill, but it's not been monotonic at all. I mean, in terms of CAM3, it was very poor. It put all model versions here, AMIP, and it's coupled under here. And essentially said it's a very poor representation of El Nino, whether you couple or not. In CAM4, we did some convection changes. There were significant improvements, although there was quite a spread. And obviously, with low resolutions for T31, for example, it was much poorer. So we thought we were on the up and up, and we made modifications in CAM5, and there was a retrograde. So it was a step backwards in terms of skill. And then more recently, we spent some time addressing some convection issues again and surface coupling. And CAM6 proves to be the best of thankfully in the whole history of the last 20 years. And most importantly, the coupled version, these B versions here, represent the importance of having coupling for the man-June oscillation. So that's a good example of coupling is important and monotonic behavior occurs. So in the last 10 minutes, I wanted to talk about a couple of challenges, 2 of many, that we've encountered in the development of CSM2. And the first one is, in some senses, the quintessential coupled, not mode necessarily, but the coupled interaction, an important interaction of the coupled system. And that's the Labrador Sea, and in particular sea ice associated with the Labrador Sea. And this has been a problem over the past year or 2 in our development, and has consumed a lot of time in terms of the biases we've tried to correct. So for those unfamiliar, the Labrador Sea here is this blue region between Greenland and Canadian coast. And of course, it's the kind of confluence of all components. You can really see it's a confluence of all components of the Earth system. So as I showed, the ocean currents, for example, the very complex boundary currents, both warm, originating from the interior of the North Atlantic, and cold along the boundary flow, the Greenland and Labrador Sea currents. And also this sea ice edge, as we can see here, retreats and advances, not a lot, but it retreats and advances during winter, during the season. And then on top of that, of course, overlying that is the complexity of the atmosphere. And one good example where particular events can have a real, impact is these cold air outbreaks. So this is a great example from February this year. So the kind of sea ice edge is under here. And there's a huge cold air outbreak of very cold, dry air that goes over the ocean. And there's massive sensible heat fluxes, 500, 600 watts per meter squared. But associated with that very beautifully are these cloud streaks that form and these unstable boundary layers that really spring up. But most importantly are these surface fluxes. So they can obviously have a huge impact on the makeup of the temperature of the upper ocean. And of course, future climate, consequences as well are important, but in the present day, there's a lot of melting that occurs along Greenland that is contributing to the freshwater flux into the Labrador Sea. And all this interaction, one of the most important components, the confluence of all these aspects results in deep convection. So here we see, and it's the only really deep convection source region in the northern hemisphere, and these yellow regions show very deep mixed layer depths, within the Labrador Sea, and also we can see this very seasonal diving of the mixed layer depth. And of course, we're all familiar, I think, with the thermohaline circulation and how that could impact future climates and the way that heat is taken up by the ocean. So that's a little bit of a drawn-out description of Labrador Sea, and it's important, I think, because when we put CSM2 together, this was one region that we had problems with, well, one of many. And here a few examples of what I'm talking about. And so these are a series of pre-industrial simulations, fully coupled pre-industrial simulations for wintertime, DJF. And this essentially is a sea ice fraction product and what the sea ice edge looks like in wintertime. And in CSM1, we did a pretty good job. In fact, it was actually more ice-free, essentially, than observations. And we can see here in CSM2, we have this big bulging out problem of sea ice. And of course, in and of itself, we could maybe deal with it, but of course, that's covering up the potential for deep convection to occur in the ocean. And the consequence of that, of course, from a meridional overturning circulation can be profound. And we have battled no end trying to really beat back this bias. And we do have a version that we have right now. We can't pretend at this point we really understand the system. It's very sensitive, much more sensitive than CSM1. And right now, we're in a situation where we do have a simulation that does not freeze over in winter, which we are moving forward with. And just to illustrate that as well, green is a different version of is a DOE model that started from CSM1, and they're having similar problems. But just to focus on the pink and the blue. So the blue here is the wintertime sea ice distribution, and it's the range of 30 ensemble members. It's very, very, very fixed at this, around 15, and so it doesn't vary at all. But in these purple examples, for example, there were spontaneous increases in sea ice that was a significant challenge to address. And we eventually, if we look at chose one of these simulations that we were able to avoid icing over. But that's just to illustrate that, this challenge, again, trying to understand the very complex system it took a lot of time. So this is only going to get more difficult with more components in the climate system. A second kind of real challenge we had was we thought we were done, like in terms of our development for CSM2 probably a year ago. And we did the appropriate fully coupled pre-industrial simulations, and then we went to 20th century. Could we reproduce the 20th century? And this red line here is our kind of reproduction of the 20th century out to around 2005 or so, and then black as a measure of observations. And it was a little cold, but we were like it's okay. We were happy with it, and we said, okay, this was with the old emission data sets of CMIP5 from the previous IPCC report, and so we said, well, we just need to put in the most recent emissions, and then we can be done and start running our full simulation. So we did that, and this is aerosol emission data sets, for example, the most important. So we put that in. Oh dear. So this is a couple of simulations where we added the CMIP emissions, and we found an incredible sensitivity to these emissions. And at first it was pretty like depressing to a certain extent, but it really did force us to go in and really understand what turned out to be sensitivities in the cloud forcing and also in the emission data sets. And over the kind of next few months, as we made modifications, we thought we understand things a lot better. We've seen this; these are all the kind of ensemble of simulations, just a select few of how we've evolved and understood more these sensitivities in a very different model. And I think it makes the model better because we understand it more in terms of the deficiencies and its behavior. So we're pretty pleased with that. And as it turned out, the major problem was in the shortwave cloud forcing. So these cloud response to increased emissions, which brightens clouds and reflects more shortwave radiation. And then we can see here the difference between using these two emission data sets is profound in these stratocumulus type regions in the eastern basins. And like I said, there were issues with the new emissions that got corrected, which was great, but there are also ways we were representing the particular cloud processes, microphysical processes, which we now understand more, but we felt were not quite right. So, all right, last 2 or 3 slides. The bottom line is, fingers crossed, 35 years of improvements. Well, yeah, you hope so, but then, and so here's my kind of very obvious plot to put up is the total annual mean precipitation. And this is our model back in 1982 here, biases, a lot of similar biases you see today, but the magnitudes are very strong. And here's where we are, we delayed, so we're in 2018 for CAM6. And so we've made vast improvements, of course, and the root mean squared error has been reduced by nearly more than a factor of 2, so it's comforting. But that in and of itself is pretty good. We spend a lot of time and money doing that, which is great. But of course, that's, going back to my earlier slide, that's on the back of having just dealing with an atmosphere back in 1982. But now all these constraints that we dealt with, the coupled system and the new components and different applications, future climate and paleo, and just maintaining what we already had, I think it is a significant achievement. So a few lines assessing NCAR atmosphere models. I hope I've given you a sense of what we've done briefly in the last 20 years and what we've been doing recently. So have we improved in the next 20 years? Yeah, I mean, DGF, I think, even though errors are small, then clear monotonic improvements in DGF. But there are persistent biases, these middle latitude precip biases, for example. New biases begin and old biases return. That's kind of problematic. And JJ in particular, ups and downs in scales. And a lot of that is related to land surface changes as well that I've not talked about here. There are trade-offs within and across components that I've not really talked about. And there are human biases. I might, maybe the MJO got better because I wanted to focus on it, and someone else didn't focus on, let's say, stratocumulus clouds in this specific group. I think the future looks really challenging, and the model for working the way we do has to change, I think, for CMIP development, and I suspect that will. Because of everything we talked about, these mountain requirements and constraints are, kind of a straitjacket, really, I think, considering the whole system. And of course, we really got to make an effort to make sure things don't get worse, and that's always a challenge when you put in new components. You are often willing to pay a certain cost by putting in new components, and that is making some things get a little bit worse. You have new science, so we have to think about that a little bit more clearly. All right, final slide. So my first thing was all models are wrong, but some are useful, and that was kind of, and the longer comment was kind of like, it's a little bit disconcerting, but I'd like to modify this and feel a little bit more comfortable, and I'll say some models are more wrong than others, but some are more useful than others. Okay, thanks very much. Thanks, Antonio. Thanks for the opportunity.
Thank you very much, Rich. That was fascinating. I think is really important because working on models may be really compelling, and people tend to be engulfed in what they're doing, and so it's important to take a step back sometimes and have a look so that one can get the perspective. So I think your talk was very useful in that sense. And now I'm open the floor for questions. We had 150 people registered for this webinar, and we have 98 people in attendance. So please write your questions in the question box, and I will try to take them up and ask Rich. Okay. Okay, maybe I'll start. I mean, there are many questions coming, so I'll just grab the first one that I've seen. It's by Melissa Kenny from University of Maryland. She's asking, if you were to design a process to improve model skill and learn more effectively, what would it look like?
I guess there's two components to that. The way I maybe read the question is that just a pure, a diagnosis approach versus a workflow approach. So I'll just address the workflow approach. So I think, as I think Melissa's responding to it, yeah, things have to change. And I think a lot of people now are focusing on how can we improve the workflow? How can we make it less human kind of oriented? And a lot of people, the big thing right now is machine learning, I think, in terms of, essentially making modifications to a code, performing a number of simulations, and then allowing machine learning techniques, which I'm not too familiar with, to make changes based on the kind of climate that you produce in the model, and to really understand how improvements can be made in an automated type cycle. So, but that's very, very new and very in its early stages, and it's not clear to me that those kind of techniques would be applied very, very soon in the future, I think. But as I said, things have to change, and I think that's one avenue for improving the workflow as it relates to improving model skill in a more objective way, and really keeping an eye on things that go wrong, things that degrade.
Yeah, that's of course is a very hot subject, and maybe we should have another webinar dedicated to it.
Yeah.
I have a question from Chaka Karinen, formerly at EPRI. He's asking, is there any evidence that the increase in spatial resolution over the years has improved model performance?
Oh, I haven't looked at that yet. That's a great question. My feeling is yes, for certain threshold increases in resolution. For example, a colleague of mine, Peter Loritzen here, kind of really determined that to get the correct baroclinic wave activity, you need at least 2.5 degree resolution. And he can pretty clearly demonstrate that kind of traversing from around 2 to 1 degree, you really see strong evidence of improved baroclinic wave activity. Now, as it relates to other features, people postulate, I think, that you need high resolution, but that it's not. I don't think there's a ton of evidence to say that. See, like I say, my area is in the tropics. That high resolution in and of itself it is able to do a better job of tropical variability, for example, because you're hobbled still with things like convective parameterization that has certain schizophrenias related to resolution, so which are hard to define. And I think, there are definitely good case studies where it works, but there are certain aspects where it does not work. But it's not across the board, I think. And it's not gradual as well. The key thing is not. I don't think it's gradual. There are certain threshold resolutions where you will see a jump in performance.
Yeah. Well, I guess nobody can expect that increasing resolution is going to be a magic weapon that will fix everything, but it's probably making things more complicated, by making the model more sensitive.
Yeah, I mean, it all goes in the basket in terms of,
in a way,
right.
Yeah.
You can have a high resolution model, but like if it takes you 10 times as much time to analyze it, then you're in trouble. Yeah.
So this leads me to a question by Malcolm Mystery, is actually from CMCC, and he's asking, so where can further improvement for reducing model bias can come from? Aren't we reached a sort of saturation point?
Yeah, I mean, if I keep myself in a job, no, but if I'm honest, yeah, to a certain extent, yeah, I agree. Well, I think it's from the traditional way we're doing things. I think I mean, it probably is some truth to that, I think. I mean, the big push on the next steps is people are not, people are thinking more about resolution and cloud resolving kind of approaches than just having a better scheme to do this or a better scheme to do that, I think. So there's a certain saturation that's been achieved. And, to a certain extent, that we're a victim of that success. We do get a lot of things right, but we're in danger of, if we move forward in the same vein, we'll get the equal amount of things right that we get wrong again. So it's, the obvious improvements in skill on average, it will not be happening.
Yeah. There's some people that are saying that we'll send you questions later. So Neale,
okay, that's great. Yeah. I'm happy to.
But I have a few more questions that are floating around. There is a question about you haven't really mentioned about the capacity of the model to reproduce long-range teleconnection patterns. So has that changed in any appreciable way? That was a question by
right. I mean, the big thing I'm going to say, obviously, is, and I was involved with a little bit back in the years, was, El Nino that we had in Cam 3 was incredibly zonal in terms of precip and the surface temperature anomalies. There's a bias typical of that time. There's a cold bias, very strong cold bias in the West Pacific, and the actual periodicity was 3 years. So we made significant changes in that. So we had the periodicity improved, and of course the location of the key convective anomalies and the divergent flow from that improved. And we did see improvement in the downstream teleconnection patterns, the PNA, for example. So that, there are, things like that are really nice because, you make a prediction that if you improve ENSO, in your head, a prediction that if you improve ENSO, then the downstream teleconnection patterns will improve, and that was the case. And we have seen, actually, the more recent stuff from the very recent version of the model, the downstream teleconnection pattern into the US is actually really good. It's surprisingly good. So, these things come in steps. So I think we've had a couple of big steps in PNA. I'm focusing on the PNA pattern here, but a couple of big steps in improved skill.
Let's see. I have a question from Laura Zamboni from formerly University of Chicago. She's asking, she's curious about your statement about all models are wrong, but some are useful. And she's asking if you would, how you would say that in a talk to a general public.
It's, that's a great question. You put me on the spot. I say all models are wrong because they don't include everything that might possibly be important. I think that's, let's say there's a very strong downslope canyon flow in Boulder here that, has very strong, important gust, wind damage kind of consequences for South Boulder here. But is that, that's wrong. So if we don't include that, that's wrong. But is that important for the use of the model, which is, is the Western US going to increase its surface temperature in the next 50 years? So that's the utility of the model is the second point, and the wrongness is the first point. So, you can finesse that obviously to a certain extent, and that's the kind of example that I can pluck out of thin air. But you're right. I think that's a dangerous statement, I think, for a non-specialized audience, and it would be interesting to pick out examples, and I'm sure other people have picked out better examples.
Well, I guess that is, is a quipping way of saying that we know that the models are not perfect.
Right.
And we know that there isn't everything there, but nevertheless, they still contain useful information.
Right.
And we know that basically they must contain some true statement about the natural world, because after all, weather forecasts are made exactly with the same technique and the same models.
That's a good way to put it. Yeah. I mean, and that's useful for that purpose, but there are things that are wrong in there. The model will drift in a weather forecast model, but you don't care about that because you know that's wrong, but the utility is in the 10-day forecast. So.
I have another question by Silvio Gualdi from CMCC. He's asking if do you think that the excess of sea ice in the Labrador Sea and some sort of coldish temperature anomalies in 20th century transient simulation are connected somewhat?
I don't think they are. I mean, you would expect it. Obviously, you would expect it. I don't think they are. I mean, if you actually look, Labrador Sea is actually a pretty small region from the perspective of surface temperature. If we went forward with that and for a longer simulation, I mean, like I talked about all the impacts of the deep ocean, maybe. But we don't think it is a kind of contributor to the problems we were seeing with the cooling in general in the 20th century now.
Thank you very much. I have another question, but I'm not sure if if anybody can answer this. It's actually a question from Lara Lazaro from Madrid, and she's wondering in what way this work can actually contribute to the Talanoa dialogue in the process of the Paris Agreement. So let's rephrase it and let's say in which way you think this can be useful for the Paris Agreement implementation.
Yeah, it's always difficult because you feel like, if you give an inch, they'll take a mile from the perspective of, saying the models are correct and we have a lot of faith in them, 90%, 97% of scientists. I don't know. I mean, I'm not involved in that area very much. And yeah, I don't know really. I mean, comes down to that statement again, all models are wrong, but some are useful. And I think it's utility, it's fair to say 97%, use this silly figure, I know, 97% of climate scientists believe that that the models are useful for this, application that is important for Paris. I mean, maybe that would be my starting point, but, I'm not a politician. No.
Yeah. Well, I think any sort of accurate or reliable scientific information is useful, is put in the right context, and then of course the negotiation will take their course and whatever. I don't have any more questions, so I will just make a sort of last call. So if people have urgent question to ask, please, this is the time.
I think people can just email, it's fine as well.
Yeah, and then of course they use email. So we'll just wait like 10 seconds. And if I don't see any more questions, then I would like to thank Rich and all the attendees for having shared with us this afternoon, morning, evening, or whatever the time zone was with us. It was very exciting, very useful. So thank you all, and having a nice day.